Okay, now we'll learn something new or something more. And this is the design patterns. So because we have learned all the basic grammars of OOP programming, now we can do something more. Play with the polymorphism, and play with abstract class, and play with these interfaces. Okay. So before that, I want you we may discuss about something on this good program. So what is good program? Someone may argue, okay, a good program should have no bugs. Is it possible for your program to have no bugs? I don't think so. I don't think so. Because most programs have bugs. Or I think more than 90% of the programs have bugs. When you have some special input, maybe your program will crash, right? And maybe in some corner that is not tested very well. If we enter some special case, special data, then it will crash your program, right? So we think we say that your program is good, and I don't think it means there's no bugs. I think it means it works for all your designed input, or for all user input. Not those magically designed input that crashes your program. Okay. If your program has no bugs, then hackers will lose their jobs, right? So this is I don't think no bugs. So anyway, our program should work correctly, right, for the input. And also readability, we mentioned about this. So we should have very good common style and have some comments and programming style and naming convention of the functions and variables and classes, objects, so that it should be easier for others to read your program, right? Actually, in our labs, our master students and PhD students, typically our students do not want to read others' code. Right? If we want them to implement some functions or do something, sometimes I would suggest our students to read someone's code and then implement over that. However, in the past, I think most students want to implement their own version of all the code. They do not want to read others' code. I think this is because the code is not, some code may not be readable actually. So if we have very good readability, we are helping others. And we are also helping ourselves, because in the future, maybe sometime later, if we want to read our own program, maybe if this is not very good readability, we may not be able to understand our own code, right? This is readability and also efficiency. For efficiency, there is a law, this 90-10 law, right? 90-10 law. The 90-10 law says 90% of the execution time of a computer program is spent executing 10% of the code. So in your program, maybe your program is very large program, actually only 10% of the program takes 90% of the time, the runtime. So this is the case. This is the case. In most cases, this is the case. So often I suggest our students, if you are, for example, if your boss in the future give you a task to improve the efficiency of some code, improve the runtime or efficiency, right? Efficiency of the code. I suggest you to use gprof first. Gprof. The gprof will analyze the code and count the number of times the function called. So we should focus on this part, focus on this 10% part, rather than focus on this part. If we focus on improving the efficiency of this part, then our program will have better efficiency, much better efficiency, right? So be careful about that, and remember that, I think. Related to this 10% and 90% law, we have another law, is 1990 law. So the 1990 law says the first 10% of the code accounts for the first 10%, the first 90% of the code accounts for the first 90% of the development time. And then the remaining 10% of the code accounts for the other 90% of the development time. That this is related to development. So the 10% of the code first takes 90% of the code takes 90% of the time first. And then someone may think, okay, my program is ending, I'm finishing my program. However, the remaining 10% of the code will take another 90% of the time for development. This is because there are many bugs, right? In the remaining 10%, the user will use your program and then, okay, there is a bug and that is a bug. You have to fix it, right? This takes a long time. I think most of our students have met with this before, right? When you write a program and then you think you're finishing your job. However, then you find a bug, then you're frustrated, right? And then you take a long time to fix this bug, right? So by following a good programming style, and this may be reduced, this time may be reduced, right? Design pattern is a good way, and also reuse is a good way. So this reuse, a good program should reuse. So because reuse actually sometimes reduce this time, because we are reusing golden code. This code do not have bugs. Okay. And this code do not have bugs. Right? So this reuse will be easy for extension. Actually, this is what we will learn later. And why reuse? This is for reliable code. Because we have reliable code, then there are less bugs, less development time. How to reuse? First one is level 0, because I don't think this is very good reuse style. Someone may be in favor of this style. We copy some code and then modify it and paste and then modify, right? And this needs source file, right? Sometimes when we write code, we typically copy our own code from this part to that part and then modify it. I don't think this is a good style of programming, actually. So a better, okay, we'll have a 5 minutes break. And Okay, let's start our class again. So we just mentioned that by reusing the code, we may avoid bugs. However, I mentioned that this level 0 reuse mode is not good. Actually, it's bad. It's not just not good. It is bad because by copy and paste and modify, it will increase some bugs, increase the number of bugs. For example, if we have this code, this is function body, I will copy this part to another part. And then we may modify a certain part, right? This part will be modified, this part, for example. However, in the future, we notice that, okay, this line should be modified. This is because maybe there is a bug, or maybe users require that we have different function. So this line may be modified. Then you have to find all the places of this line and modify all the code, right? If you miss one, then there will be another bug, right? So this copy, paste, and modify is really a bad programming behavior or programming habit. Try to avoid it. Try to avoid it. A better reuse is to use composition inheritance. Because composition inheritance, by doing this, we are not modifying the base class, right? We are not modifying the old class. The base class is not modified. We just reuse it. And this class is golden, right? It's already tested. No bugs, right? Works correctly. So by this kind of reuse, we can incrementally develop some function very fast. Is there another higher level reuse? Actually, yes. So this is the reuse of design experience. So this is design pattern, right? Called design pattern. So by design pattern, during software design stage, we can make future extension easier. So actually, this design pattern or design experience is used to design the software software structure, right? Software structure. So by doing this kind of software structure design, we can easily modify some part or easily incrementally develop the software. Because sometimes user is not satisfiable. Right? They make requirements in one day, and then we finish the code, and then another day it will make another requirement. We have to finish to modify the code more, right? And then another day it will make more requirements. So user requirements may change. So how to design our software so that it will be easily modified or extended for future change. And this is the key. So this kind of design experience is very useful for developing software, and this is called design pattern. Okay, so we are following design pattern, or sorry, we are following patterns in our everyday life. For example, for this building, we always first build the foundation, right? 所以这个地基不牢，基础不牢，地动山摇，对吧？Foundation is the most important part, right? And then we will build this steel structure, and then concrete structure, and then declaration, right? So this is a pattern, right? We are always following this pattern to make a building, right? And also there's also some saying that so all happy families are happy alike. All unhappy families are unhappy in their own way. 幸福的家庭都很相似，不幸的家庭各有各的不幸啊。 So these are patterns, right? These are patterns. So we are following patterns everywhere, actually. So why not programming? Why not programming? So there is a architect in his report. It says, so each pattern describes a problem that occurs over and over again in our environment, and then describes the core of the solution to that problem. So in such a way that you can use this solution a million times over without ever doing it the same way twice. Right? So this pattern, right? You find the pattern, you use the solution, it's done, right? So for programming, design patterns are invented by this gang of four. Right? These are the founders of the design patterns. And they have the Bible book, right? So that is our reference book. So the OOP language and also Java are good languages or suitable languages for implementing these design patterns. And also by this inheritance, polymorphism, and composition. And these are the keys, right? These are the keys for enabling design patterns, right? Design pattern is these are the key, right? These are the keys, sorry, like this. So because we have learned inheritance, polymorphism, and composition, so we can easily use design patterns, right? Or define. I don't think maybe some students may in the future may invent some new design patterns, maybe, but it may not so easy, right? It may not be so easy. Anyways, we can memorize these golden design patterns and recognize places in our applications so that we can use these design patterns. Okay, so by learning these design patterns, this is a kind of strengthen our understanding of this inheritance and polymorphism, and also we have more knowledge or backgrounds on how to design software. Okay, first one is creational design pattern. So this creational means it will create objects. Okay. So here's an example. We already learned this before. So if we want to create a single example, there are typically two ways. One way is on stack, this local object, and another way is on heap. We use new. If we want to create arrays of objects, there are still two ways. One is on stack, like this. There's local variables, local objects. And another way is to use new, again, by this brackets, right? We can define or allocate array of objects. And how to control the numbers of this singleton, the objects for a class. Why should we control the number of instances for a given class? This is because, for example, there are such applications. So, for example, typically a system only has one printer, right? So if we have a class to access the printer, then it should have only one object, right? One instance, because we have only one printer, right? If we have multiple objects, then there will be conflicts when access this printer, right? So this is one application scenario. Also, another one is program configuration class. So for many software, or applications, and there is a configuration file. In this configuration file, there are different parameters to tune this software. So when we start this software, this configuration file will be loaded automatically. So this program configuration class will load this configuration file. Because there's only a single one configuration file, we know that we only need one instance for this class, right? So this is another case. One more case is the GUI programming. In GUI programming, we know that, for example, we can use in Word. This is GUI, also GUI programming, Word. In Word, we use if we want to find something, we use this to pop up the search dialog, right? So we do not want to pop up many different search dialogues if we want to search in one Word document, right? So this search dialog should be popped up only once, right? So in this case, we should have a single instance for this search dialog, right? So this is another case of using singleton design pattern. So the singleton design pattern is to ensure that a class can only have one instance of global point of access. So we have already learned this before. So this class egg and by static member and by setting this constructor as private, then we can avoid the construction or the constructor call for creating the objects. Then we can use the static interface to access the single instance, right? So this is the basic idea. So for reviewing this idea, so there is an example for this singleton. If we only set constructor as private, then we know that we can do it by copy constructor, right? So we should set copy constructor as private. For this assignment, this is actually this assignment is to avoid self-assignment. If we set the assignment operator as private, then we cannot do this. We cannot do as equal as. We cannot do this. And this avoids this self-assignment. And also, so actually this we now use a pointer, right? Now we use a pointer. Why should we use a pointer? Because in our previous example, egg, we know that it has a static instance, right? The static instance will be initialized early before this before the call of the function, I think, in most cases, right? So for this, in this case, this static instance will be created no matter we call this function or not. This object will be created, right? However, if we want to, because sometimes we do not need this instance. For example, if we do not want to access printer, we may not want that object to be created, which takes memory, right? So this is the reason why we have this pointer member, right? Pointer member. Then when we want to access the object, we will check whether the pointer is 0 or not. If it is 0, then we create an object. If it is not 0, then we just return it, right? So in this case, actually in this example, it still does not work because it works sometimes, but it's not very in corner cases it will crash, right? Because, for example, if we get a pointer here and then we delete it, then we get the pointer again. What will happen? Result is unpredictable, indefinite, right? We don't know. Probably it will crash, right? Because in this case, if we delete it, and then the pointer, if we delete it, then the pointer points to some freed memory, right? However, the pointer is not zero, right? Pointer is not zero, so the pointer will be returned, right? Will be returned here. And this pointer S points to some freed memory, right? This is unsafe and unpredictable, right? So how to solve this problem? So we can so here we can set the destructor as private. So in this way, we can avoid the user from deleting the pointer, right? If the user delete the pointer, then because the destructor is private, then companion error will occur, right? We cannot delete the pointer anymore. So if we do not need to free the resources, then it will work, right? However, if we want to, if this, for example, this object takes a large memory, after using this instance, we know for sure that we will not use it anymore or any longer, then we may want to delete it to save memory, right? However, this is not deletable, right? We cannot delete it. How to do that? So there are more complicated designs using CVV language for this singleton design pattern. If you are interested, you can try to find something more. Okay, and also we have not mentioned about the move constructor, right? The move constructor we did not mention. You can also think about this. Right? Think about this move constructor. I think for the move constructor anyway, because the move constructor we still keep one instance, right? So maybe it's not so critical because we are moving from one instance to another, right? Okay, then this is the singleton design, the class, and then actually this is a class diagram. Yes, UML, right? Called UML class diagram. So this is how we denote a class, and then this is a class name, and then this is a member function and data. So this is how we typically represent a class graphically or visually. Right? This class name, member function, and the data member. Right? And this is the implementation. This one. So this is a unified modeling language class diagram. So typically we use this to demonstrate the class relationship between classes. Okay. Now we'll learn this adapter. So adapter is a structural pattern. So singleton is a creational pattern, which is create the objects. Structural pattern gives some structure or interface between the different classes. Right? For example, for example, if this class is like this, then this class may look like this. Right? Then we will get some structure to stick the two parts. Right? So this the structural design pattern considers the structural relationship between the different classes. Okay, so this we will learn this adapter design pattern. Our example is a stack. So how to write a stack? So stack, we know that stack is last in, first out, right? Last in, first out. Then if we want to have a 10 element stack, then stack typically have these interfaces, how to push in an element, pop an element, get the top element, whether the stack is full or not, and checks whether the stack is empty, and get the number of elements in the stack. So here is how we how the user tests the stack. So although the stack is not implemented yet, we still can write a testing program, right? So this is also called testing-driven programming. Testing-driven programming. Right? Then for this testing-driven programming, I want to mention something more. So typically, I think for most of our students, especially for those students who have attended programming competitions, maybe you are used to write functions like this. Maybe there's 100 to 1,000 lines of code, right? This function body is very long because when we do programming competition, we want to save time, right? And all the lines in one function body saves runtime, right? We know that. So we are used to do this. However, this is not good for software development. This is not apparently this is not good, right? So we call this flat mode coding, right? A better way is that try to, for example, if this is very complicated function, actually may consist of several steps, try to modularize, right? Modularize this. When we write this f function, then maybe we write several lines. Now we know, okay, this part should be a function, right? Should be a module, right? F1, right? And after calling this function, we can do this, right? This may represent 200 lines of code, right? 200 lines of code will finish this module, right? And then we write again. Now we know that, then this, for some students, maybe when we reach here, he will go to implement this F1, right? And then after writing this F1 code, then go back and then write the program again, right? Then it may, okay, then there's another module, F2, and then go to F2. After writing F2, come back and then write again, right? Like this. So this, I call this, actually this, I call this top-down programming for F, and then maybe there's the F1, F2, and then in F1, maybe when you write F1, you are still going to other parts. Maybe you are going to F6, F3, F4, like this. So after writing F4, you come back to F1. After coming back to F1, you come to F2, right? Like this. So this is, if some of you may have learned this depth first search, right? So I call this a DFS top-down coding. this is my name, my name convention. I want to name this as DFS top-down coding, right? DFS top-down coding. I still don't think this is very good because when you write this, you have to think about how to write this, and then when you write this, you come here, then your thought is breaked up into pieces, right? You after you come back here from this F1 function, you may have lost your original idea how to implement this F function, right? So a better way is to write F function and then you know, okay, here is some module I need to implement. Okay. Then you assume this module has already been implemented. And then you just write the following part. And then you identify this another part, F2, then going forward. And until you finish F function, then you go to implement F1. Okay. Then again, if you identify some module, then write the remaining code and identify further more modules. Okay. So in this case, and this is BFS, right? We are following the BFS top-down coding, right? Top-down coding. So I suggest you to follow this BFS top-down coding when you do this software development. I mean, when you are not doing programming computation. Right? And this is a good way because it saves your time, and you do not need to be your thought will not be break up into pieces. 就是我们这个思路不会打断，对吧？就我们要实现这个 f 的 function， 结果呢，我的这个思路我一下就留下来哈，就我知道这一块是个比较难做的一个功能啊，这个需要200行到500行程序，但我现在就可以先用一个函数或者一个对象，对吧？代替它就可以了啊。然后我直接去写下面的程序，然后又看到一个比较复杂的功能，我又写一个 module， 我就假设这块就已经完成了，继续往下走，对吧？这样的话，我的思路不会被打断。我要实现这个功能，整个下来我就完成了。等整个这个实现完之后，我再去实现这每一个小的片段啊，这个 module 我再重新实现，然后又分出一些小的 module 来，对吧？然后又去这样实现。这样的话呢，我们就不会觉得一个复杂的功能变得非常非常难以实现。因为我们已经把这个像通过我们的思维的这个组织啊，把这个问题已经分解成一块一块的啊。然后呢，又不会说一下像前面这个 DFS 这个 top down 的话呢，我们又要我本来就思维在这儿转呢啊，我本来要实现整个这个功能，结果我去实现 F1， 然后又想 F1 怎么实现，结果原来的思维就断掉了啊，就忘记原来到底要做什么，又要重新想重新思考。所以的话呢，我个人建议啊，就是说这个 BFS 的这种模式啊是最好的，就我们要实现一个复杂功能，通过 BFS 这种方式来实现啊，应该是最有效的。Okay. Anyways, this is up for open for discussion, and this is my understanding and my suggestion. If you have different ideas or different suggestions, you can discuss with me. Okay. Okay. Then so actually, this testing-driven programming is similar to this DFS. Top-down programming, similar to this, because we assume main stack has already been implemented. Actually, it is not, right? So we assume it's already implemented. So we write this. Okay. So this is also for implementing this f function, we assume this one is already implemented, right? Actually, it's not the case, right? However, this skill help us to partition the original task into smaller ones, and then finish each one separately. Right? It makes our task easier. Okay. Okay, then now come back to our problem. How to implement my stack? How to implement my stack? This is one solution. It's very simple solution. We use an array of integers, and then we use a pointer. Actually, we use integer to point to the top of the array, and then we can check whether it's full or not. And also we can push one by modify the pointer. So I'll now go into detail. After that, we may think, okay, we have learned STL, right? We have learned STL. Why not use STL stack? You want a stack. I know that STL stack works very well. Why not use that? Also, STL vector also works, right? Can also be used to implement such a stack. So why not use it? Then we have another solution using this STL stack. So we just use STL stack. We can easily check whether it's empty. We can also easily push in one element like this. So only the interface may be a little different. However, for example, top, we need to further check whether we have one or not. Only the interface, the interfaces are similar and the implementation are similar. We just adapt this STL stack to this stack, right? Also for STL vector is similar, right? So now we have 3 implementations of the class myStack, and we want to use the first one is use built-in type, another one is STL stack, also STL vector. Right? So for STL stack and vector, the interfaces and the functionalities are very similar to the original problem requirement. We just plug and adapt these already defined objects to the user program. So now we want to reorganize the program. We want to have a base class as a base stack, and then we can define different stacks. The one with STL vector and the one with STL stack can be defined. We use different classes to define this. So in this way, we are by accessing the base class, the interface of base class, we can access derived class interface, right? Derived class interface. So the source file may look like this, because actually this is the interface. So we do not need to implement the function body. And we just give the interfaces, right? Interfaces for other program to access. And then this is concrete class or derived class. In this class, we can implement the interfaces. Also, vector stack is similar. Then it works. So by this example, we want to mention that we are accessing interface. We are accessing the interface by base class. So this actually this abstract class, we know that abstract class cannot define objects, so it only provides some interface. The abstract class is also called interface class because it provides interfaces for other users. By doing this, we can easily use different derived classes without writing another test. For example, if you write a test, originally if you write a test of a vector stack. If you write this, then you need to write another, right? You need to write another test for stack, right? However, if you write a test for basic stack, that's all, right? That's all. You only need to write one function body that works for all different derived classes. So this is the key, and this is the benefit or merit. Okay, then this is very important OOP design principle. That is, program to an interface, not an implementation. So an interface is a concept borrowed from Java programming language. It is similar to C++ abstract class without member data, because the abstract class, in this case, only provides the interface. So when an abstract class only provides interfaces by pure virtual function declarations, we call it an interface class. We mentioned that. So by overriding virtual functions, we obtain derived classes called implementation classes. So one interface class may correspond to multiple implementation, one interface class or base class may correspond to multiple derived classes or implementation classes. So we should use class family by interface class, use it by interface class, so that it will be extensible for future change. What does that mean? For example, here, because we access the class hierarchy or class family by this base class or interface class, in the future, we may have another stack. For example, we may have a vector stack, a stack, we may have a list stack, right? We use stl-list to implement this stack. Then we just test it directly. We do not need to modify this test function, right? No need to do that. So this is the merit, the benefits of accessing interface class. Okay. So programming to an interface is very the number one OOP design principle we should follow, or we should memorize, and we should use. Okay. Then another one is the open-close principle. So actually, the open-close principle means software entities, classes, modules, functions, etc., should be open for extension, but closed for modification. Open for extension means add a new code. Closed for modification means we should not modify existing code. Okay, so we add new code. So when the requirements change, we add a new code. We do not modify original code, because modifying original code may cause bugs, right? Because original code should already be tested, works well. If you modify original code, there will be bugs. Maybe you introduce bugs, right? So closed is that we should not modify original code. So by programming to an interface, we have the effect of open-close principle. So these two principles actually has some cause and effect relationship. By following programming to an interface, we have the effect of open-close principle, just like the stack example. Right. So originally we want a stack, and then already have a STL stack and vectors and STL vector, and they have similar functions and interface. So we can just create an adapter class to convert stl stack and vector to the required stack. So this is the adapter class and the adapter design pattern. So in the adapter design pattern, we can see that we access base class or interface class, right? Then we have this adapter class, which adapts stl vector, right? Adapts stl vector, and use stl vector function to finish the required function, right? So this is adapter class by composition because these are the members, right? Members. This member and data is a vector, right? This is composition. So here is an inheritance and here is an composition. So this class diagram is adapter design pattern. Intuitively, it's like this. So actually, we know that we should not travel these days. But for those who have went to Europe before, we know that the outlets have different styles, right? So our style, our plug may not work on this wall, outlet. So if you travel to Europe or travel to other countries, first check their outlet criteria or standard. Prepare the power adapter before you travel, right? So this is adapter, right? We are adapting from our existing system, and sorry. So you have this vendor class is STL, for example, STL stack, and my existing system needs a stack. The interface may be similar to this, but maybe some tiny difference between them. Then we can create adapter class to adapt STL stack to this, our needed stack. Okay, and this is adapter, right? How it works. Right? So by doing this, we are actually adding new code. Original code, no change, and the original code, no change, right? We just plug them together. Right? It works. So this is the adapter design pattern. And also this is a more general object adapter class diagram with inheritance and composition. So by accessing the target, this is base class, we are programming to an interface. So by program to interface, we follow this open-close principle because we are adding new code. We are adding this new code. We are not modifying old code. Okay, due to time limit, I think this example may not be finished in time. We'll have a quick look on this. So this is a viewer system example. We have a class C shape, and also have different shapes like this, and then we have the view, which is also the class of C shape. And we have this in the view, we have a vector of C shape. Then in the view, we can draw all the shapes. Then if we want to draw text, how to do that? We have some third-party class which can draw text. Then we can add a new adapter class. Like this. This class will adapt from this text class, third-party class, to this to our requirement. Okay, due to time limit, we do not have time to finish this. I hope you to learn this after class. Okay, okay, that's all for today's class. Thank you. Bye-bye. Start our class. In our last class, okay, let's first come back to our one of our previous questions. So in our previous classes, some students asked this question for this mu, right? For this mu. So how can it work? How can it work? And why the object is not invalidated? Why the object can still be passed after this construction of the parent object? Why we still can use it? So for this question, we first check an example. Lecture 8. So in this example, we can see that we actually this example is very similar to the one in the slides. We have the parent and we have the copy constructor and the move constructor for parent, and then we have the member class which also has the copy constructor and the move constructor, and then for child we have the copy constructor and the move constructor. So we test one case like this. So we define a child object, and then we assign the child object to the parent object. So in this case, we know that the constructor will be called, right? Because we are defining a new object. So constructor will be called which constructor? So apparently a copy constructor will be called, right? So we are using child object to initialize a parent object. So this is a very special case. So another test is the move constructor call. We are using a child object to initialize a parent object again. And because we call the move function here, so it will the C value will be used as a R value reference, and the move constructor will be called for parent, right? This is our assumption. Let's check. So from the results, we can see that after calling the copy constructor, the parent copy constructor is called. So, and after calling the move constructor, the parent move constructor is called. So we can see that only the parent constructor is called. The child constructor for child is not called, right? So this means the parent part of the C object is called, right? And the parent part of the C object is moved, right? So from this example, we know that although we are using a move here and we are using child object here, only the parent part will be copied or moved when the parent's copy constructor is called. Constructor is called. Okay, so from this example, we have this conclusion. So Now we can understand this, right? So if we are initializing a parent object from a child object, actually the child part, right? The parent part of the child object C will be moved to this parent part, parent object. So the member part of this object C is remained, right? So by the parent part is moved, we mean that, for example, we know that we have defined, this is very simple example. Okay, let's draw a picture for this. So for this child object, we have some parent data. For example, there may be a PTR, a pointer, which points to another memory. And there's also member part of the data. Then by calling this move, this part will be moved to the parent, parent object, right? And then this PTR will be set to 0, right? Null pointer, right? Will be set to 0. So this part is invalidated. We cannot use it anymore. However, this part is remained after calling this. This part is remained. So that's why we can do this. Okay, so this is the answer to our previous questions in class. Okay. Then come back to our so in our last class we learned this viewer system, and we have learned adapter design pattern. So this viewer system example is to demonstrate how we use adapter design pattern. So in the viewer system, we have the C shape, which is the interface class or base class. And we have also the C shape, and we have some implementation classes, C rectangle, C square, C circle, like that. And then we have a C view, which is also a subclass of C shape. So in the C view, it consists of a vector of C shapes. Because in C view, we can still draw. So in C shape, it has a draw interface. And then in the C view, we still need to draw, right? We still need to draw. And in this C view, if we want to draw all the shapes, we just enumerate all the vector elements and call it draw interface. So here, we know that these shapes are rectangles, circles, like that. So polymorphism works here, right? Polymorphism works here. We can also add a shape into this vector, right? So this is C view. And then there's a third-party class, C context. Which has a draw text. This is the interface class. And then there's a subclass, implementation class, C text, which do the real text drawing jobs. So how to use the third-party class in our viewer system? So this is a problem, right? Our solution is to use adapter class. So we define an adapter class without modifying the context, the third-party classes. We just adapt it, right? Adapt it to our viewer system. So this is the adapter class, which is a subclass of C shape. And then this draw function is overridden. this draw function is overridden. Okay. I think okay. Anyways, let's go on. I think my cell phone, the controller is something wrong. But anyway, I think if you have any problem, please open the Zoom and you can just speak to me and tell me what happens if something wrong from your side. Okay. So in this adapter class, we override this draw function, and then we draw the text. And here we program to interface, right? Program to interface because this is interface class, and actually we use this to draw the text. Right? Use this pointer to draw text because this is interface class, right? Interface class, abstract class, and this is draw text, right? So we always program to an interface, not an implementation. So this is our number one rule in the OOP design. We always think of program to an interface, okay? Then we are programming to interface, and we have the base class pointer here, and we use the base class pointer to draw the text, okay? So this is the adapter class. We adapt the context or the text drawing classes into the viewer system, because we have this C shape text, right? C shape text. Then this C shape text can be added into the viewer, right? By add shape, right? Because it is actually a C shape, right? So the viewer, the C view class can add any C shape subclasses, right? Subclass pointers. So we can add it into the viewer, Then we can draw it. Okay. So this is the object adapter. Actually, this is composition here. We are using object adapter, adapt third-party classes into our viewer system. So actually, we have some we have the code. The viewer system. So sometimes you have this and found a swap file by the name .main.cpp.swap. This is caused by the viewer. Sorry, this is caused by the editor, the VI editor. So if you LS files, you can find, okay, here is such a file, right? So this file, if you sometimes if you your VI is crashes or if you are already opened this file, then there will be such a file. This is editor generated file. Then you can actually you can safely remove it. And that's fine. Okay. After that, you can open the file again. Then this is a viewer, so we can have the C view, and then we can add any C shape pointers. This is C rectangle, and also C square. Actually we know that because we already generated a C circle, for example, C circle pointer. If we do add shape, we are doing upcasting, right? We know that, right? We are upcasting from C circle to C shape pointers, right? So upcasting works here, right? Works here. So this is how we use the third party class, because we already defined an object adapter class. So we use the object adapter to adapt the third party class. And then we can add the shape, right? Shape text. Then we can draw it, right? So after that, we can see that it works fine, right? You can successfully draw the text on your screen, right? So actually, we will learn the GUI programming in the future. For the GUI programming, this is graphical user interface programming, right? Graphical user interface, right? GUI programming, and the texts are drawn to the screen, just like what I'm doing now, right? Are drawn to the screen. It is completely different from our current code. Currently, the texts are printed to the screen, right? Printed line by line, right? Line by line. This is line by line. So this is one line, this is another line. So if we press enter, there's another line. So this is line by line. You cannot print it to another place, right? You cannot print it, for example, half line. Not possible, right? It's impossible. So this is complete difference between the GUI programming and our current programming, right? It's completely different. Okay, so we will learn this GUI programming in this summer. Actually, it's based on Qt, right? Qt programming. This is the Qt library is all implemented in C++, actually. So this is based on the C++ CPP language, especially inheritance polymorphism. We need to learn this better so that in the summer it will maybe easier for us to understand how Qt works. Okay. Then this is class diagram of the this viewer system, and we have this C shape base class, and C view actually is also a derived class of C shape. However, in C view there is a vector of C shapes, right? Sorry, okay. Vector of C shapes in C view, and then there's a draw function, right? There's draw function that overridden in C view, and then in C view we can enumerate all the C shapes, then draw all the shapes, right? Then we have an adapter class C shape text, which adapts a third-party classes into this C shape, right? Then this C shape text is also added into this vector. Then we can draw it. So this is how it works. I think this is a classic design for this this kind of applications for this C view, which is also a subclass of C shape. This is interesting design, right? And it works fine. Okay, and this is a viewer system. Okay. After that, actually we have learned this object adapter. Object adapter means we are adapting the third-party classes by objects of the third-party class, which is composed into the new class, into the adapter class. So composition works here, right? So that is adapter class, adapter design pattern using object adapter. However, there's another type of adapter, which is called a class adapter. So class adapter is to adapt by class inheritance. So originally, this third-party class is as a composed component or composed into the as a member in the adapter. Now it is a base class, and base class of this adapter. Right? This inherits from this adaptee. Right? This is class adapter. So multiple inheritance is needed here because this adapter class has two parents, right? Two parents. So this is class adapter with multiple inheritance. Okay. So if we adapt a third-party class by class adapter, it works like this. So originally we inherit from the C shape. Now we have another parent class, C text. Then when we want to implement this draw function, we can just call draw text, which is this function, member function in C text, right? So this is a way to reuse to implement how the draw function is implemented, right? So this draw text is here actually, draw text here, and then in draw text we can call the C text draw text, right? Draw text. Then it will work fine, right? It will work fine. So anyways, you can do something here if you want, because after calling this draw text, maybe you want to do something more. That's fine, right? That's fine. Then this is how we test it. This is similar, C shape text, and then add shape. Then we can draw, right? We can draw. Okay, then this is a class adapter. After that, we will learn something on this. After that, we will learn this simple factory. Simple factory. Let's start another time. Okay, I think let's start another time because I think something for the ring class something is wrong. Sorry about that. This happens because when we switch between the different ring class slides. Okay. Now we will learn something on this simple factory. Simple factory. So this is another design pattern. So this is also called belongs to creational pattern because which is similar to singleton. Singleton is also a creational design pattern. So simple factory. So for simple factory, there is an example. There's a story actually for this pizza store. So there's more pizza store in the small town, and they only sell one type of pizza. Right? One type of pizza. So this is easy to implement. We have one type of pizza, class pizza, and then we have the order pizza function in the pizza store. So we can order this pizza, and then we can sell this pizza, right? So this is the initial design of this pizza store. However, the pizza store grows larger and larger, and we want more type of pizza, and they want to sell more type of pizza, right? So how to do that? So because we have learned this key design principle, which is program to an interface, so we will think of designing a class hierarchy, right? So we have this interface class pizza, and then in the pizza we have this cell pizza, right? Then we have different type of pizza, cheese pizza, which overrides this cell pizza. Actually, we will only print something. However, this part should be much different because making cheese pizza and making cell pizza are very different, right? Making veggie pizza, cheese pizza and veggie pizza are completely different. So this is how we design the pizza inheritance hierarchy, or the pizza family. Now we can order more type of pizza, right? We can add one parameter here. So based on the parameter, we know which pizza we want, right? So this, if the type is cheese, we can order get a type cheese pizza. If the type is veggie, then we get a veggie pizza. However, please be noted that the returned pizza pointer is the base pointer, right? Base class pointer. So this base class pointer means we are programming to an interface, right? We are programming to an interface. So in this case, we can return cheese pizza pointer, veggie pizza pointer to this pizza pointer where upcasting works, right? So in this case, we do not need to worry about the type of the return type, right? We do not need to worry about that. We always return a pizza pointer, that's fine. And also because we have this interface for the pizza, we can do this. We can call this pizza's cell pizza interface. It works fine, right? So in this way, by programming to an interface, this part will not change. Even we add one more type of new pizza, one new type of pizza, this still works, right? We can add something here, still works. So if we want to add one more type of pizza, let's check which part change and which part does not change, right? So apparently, in this part will change, right? And this part will not change, no change. This part will change, right? So if we want to add one more type of pizza, this part changes, right? And this part without change. So be careful about that. And in our design, we should always think of which part change and which part does not change. If we are sure that some part changes and some part does not change, we should separate between the two parts, right? By separating that those change and those not change, we can avoid potential bugs. For example, if we want to add one more type of pizza, we just need to modify this part, and if this part is separate, from this part, then we can avoid some potential bugs by mistakenly modify this part, right? And also, it makes the task easier for us without reading all the code to find this part, right? So we should always be careful about which part change and which part does not change, right? We will also talk about this later. So in this pizza store problem, pizza is an interface class, and cheese pizza, veggie pizza are implementation classes. So we follow this program to an interface principle, and then pizza, the cell pizza does not change, right? Does not change. Even we add one new type of pizza, it does not change. So this is the merits of this program to an interface, right? Sorry. Merits, right? Merits. If we add one more type of pizza, we can do this, right? We can do this. We change this part, right? Here we add one salmon pizza, right? So, however, if there are many different versions of order pizza in different stores, for example, order pizza 2, order pizza 3, there are many functions with the same function body like this, similar function body like this. Then we have to modify all those functions, right? This is error prone, right? So we may think of separating the two, right? Separating two parts, and use one function or use one class to do this, right? So we can first separate those two, this part and this part, into one function named cook pizza. So this pizza is to mix the pizza, and another part is order pizza. So this is order pizza. I think this is okay. This is first we cook pizza, then we sell pizza, right? So if in the future we want to add one more type of pizza, we do not need to modify this, right? Because this part is programmed to interface, and we just provide the type. It's fine, right? So and also this is also programmed to interface, so we do not need to modify this part. So this function will not change in the future if we add one more type of pizza. We only focus on this. In all the order pizza, maybe there's also order pizza 2 and 3 like that. And because this part does not change, we do not need to modify those functions, right? So we only need to modify this single function that works. So this is the merits of separating those changes and those does not change, right? So from this design, we can see that we assign the pizza cooking task to the pizza cooker. We can because originally we have this cook pizza function, right? Now we can use a class to do this. Right? We can use a class to do this pizza cooker, right? So for this class, we have a product. This pizza cooker generates pizzas, right? Generate pizza. So the pizza cooker now is a factory to manufacture products, right? Manufacture products. So this is a cook pizza function. Now we have a pizza cooker, right? Pizza cookers. Now we have the pizza cooker class, right? Pizza cooker class to do this. And we can call it a factory, right? We can call it a factory because it generates objects, right? It's manufacture objects. So it is actually a factory. So this is actually a simple factory design pattern, and there is an interface class product with a family of implementation classes: veggie pizza, salmon pizza, I think cheese pizza like that, and this interface class is pizza. So simple factory manufactures these products with parameters to determine a concrete product. Which pizza do you want, right? You can just provide the parameter. So this factory generates a family of products, right? So in this pizza store example, pizza is an abstract product, and this cheese pizza, Wagyu pizza are concrete products. And pizza cooker is a simple factory. So this is a class diagram. You can see that we have a class hierarchy of the products. This is base class. These are the concrete products. And then we have a simple factory, which takes some parameter to determine which part of product do you want. Then we can create corresponding product, right? However, because we are programming to an interface, we always return product. Some parts will be saved because some part may not change, right? We just demonstrated that, right? We know that some parts do not need to change because we always program to an interface. And we do not need to worry about the member function objects create because we always generate different objects, right? However, by upcasting, we always return the product pointer. It works, right? Otherwise, we have to, we cannot have one function, right? Because we have to return different products and different types, different object types. So this one function does not work, right? It's not possible. But by return this interface class pointer, then it works. Okay, so this is class diagram of the simple factory, and here the complete code. We have this in the system. So from simple factory, so we can open this file. Okay, again, there are some. Okay. So sometimes if you open too many files together, then sometimes this is kind of annoying, right? So anyways, we have opened this. So first let's check the pizza header file. So in this file, we can see we are defining an interface for the class hierarchy of pizza. And then we have this Wagyu pizza. So this cell pizza function is overridden. And then we also have this cheese pizza. So like this. Then we have this simple pizza factory. So in this simple pizza factory, we use the enum type to determine which type we want. In future, if we want to add a salmon pizza, we have to modify this type, right? And then we also need to modify this create pizza, right, function. So based on the type we want, we generate or create the pizza and return the pointer, right? Return this pointer. So you can see here, originally we have a pizza pointer, and then the pizza pointer, the cheese pizza pointer is assigned to pizza pointer, right? So we are doing upcasting here, right? So this is programmed to an interface, right? Programmed to an interface. By programming to an interface, this pizza store will not affected if in the future we want to add a new type of pizza, so we can see that in the pizza store, we only need to pass in the factory, pizza factory, and then when we want to order pizza, we just give the pizza type, then it works fine. So if you want to add a new type of pizza, this pizza store will not change, So by separating those changes and those that those do not change, then we can avoid this. We can avoid modifying this pizza store. Okay, so then in main, you can see that we have this simple pizza factory. We first make this simple pizza factory pointer, and then we construct a pizza store. Then we can order pizza like this. Okay. We can run it, so we can get a correct answer. Okay, then this is a simple pizza factory and a simple factory design pattern. So we have one question here. Does simple factory comply with the open-close principle? We will answer this in next class, okay? So we have learned singleton, adapter, and the simple factory. Actually, singleton and the simple factory are creational design pattern, and the adapter is structural design pattern. And we have learned this program to an interface. This is #1 design rule for OOP, right? OOP design rule if we want to design software. So that we always program to an interface, not an implementation. So implementation means subclass, right? So interface means base class. So we always use base class pointers, right, or reference. We do not program to an interface. We do not program to an implementation. We do not use derived class. By doing that, in most cases, our design will comply with this open-close principle. So this is a key. Right? This is a key for, I think this is the key for design patterns. Okay. Then we will learn some new design patterns.